Hello everybody and welcome to the next edition of NPTEL online certification course on microelectronics, devices and circuits. In our previous modules we have actually seen differential amplifier using bipolar technology and we came to a major important issue that all common signals are being rejected and all differential signals are getting amplified. Common signals primarily mean that noise signals are getting rejected and all your differential signals, which are the input signals given, will always be amplified. This results in one important parameter known as common mode rejection ratio, CMRR, higher, which is defined as the differential mode gain ratio of the differential mode gain to that of the common mode gain. So, it is basically AD by AC. Just to give you an idea about what I was talking about in your previous discussion. Just to remind you, because we will be starting from where we left in our previous turn and we will see how it works out in this case. So, we had defined another term that it is known as CMRR, known as common mode rejection ratio, and we saw that this to be equals to AD by AC. We do not take the sign of it, but it is differential gain upon the common mode gain. Now, typically since AD is large and AC is very small, right, because the idea is that the common mode signals needs to be suppressed and therefore amplified less as compared to your differential mode your design, and that is the reason your CMRR are relatively very high, right. So, this is one of the design criteria we generally follow in an amplifier, that especially in our differential amplifiers whose CMRR should be high. So, we understood two things, that AD should be high and AC, the common mode signal, should be CM should be low, right. To do that, we first bias the device in a BJT in the active region and we do not let it go into the saturation region, but we go from active to cutoff and cutoff to active, because we want the switching speeds to be higher. So, if you take a bipolar technology, right, bipolar technologies have typically very small switching times, very small time, or its frequency of operation is very high, right. Its frequency of operation means the frequency by which the switching can take place is very high, and this is one of the major advantages of bipolar technology. What we will do in today's lecture is we will replicate the same thing which we did in our earlier design in our earlier bipolar technology, and we will try to have it through MOS technology, because CMOS is the standard sort of industry standards, and therefore what we will do is we will just look into the following outline of the talk. We will look into the MOS differential pair, how a MOS differential book looks like. What do you understand by differential half circuit? We have already seen it, but we will see it in details. Then we will put a current source load at the output and see how it works out. Then we will look at the cascaded differential amplifier, CMRR, the meaning of CMRR with respect to CMOS technology, and then this comes with the fact that your till now we were all assuming that the resistances in the left and right arm of a bipolar technology based differential amplifier are exactly symmetrical, which means that both the transistors of both the bipolar will have the same value of beta alpha, will have also the same value of the drain resistance RD. In such a scenario you are able to reject the common mode noise very easily, but in reality when you actually fabricate, you will always have certain mismatches in the transistor in terms of its transconductance as well as the drain resistance RD. So, that we will be studying in the next two slides or the next two sections, that is RD mismatch and GM mismatch. So, we look at these mismatches and see how does it affect our overall picture as far as the small signal operation of MOS device is concerned. Let me come to the small signal operation of a MOS device, and as you can see here, what we have done here is that, please remember from our previous discussion that whenever you did have a common mode signal, right, we told to you, we discussed the fact that a common mode signal will always give you a zero differential output, right, and the reason was very well known to us, because the same current was drawn through both the arms and therefore the voltage drops at the output were exactly the same. If you subtract two equal quantities, you always get a zero voltage. Now, if you look at this left hand side slides, you will see that what we have done is that we have given an gate voltage onto the gate side, of Q1. We are here assuming that Q1 and Q2 are two symmetrical transistors and RD is also the same value which is in the left and right arm. Under such a scenario, if I give a differential input, then VID is defined as the difference between the VGS1 minus VGS2, right. So, the difference signal is given. So, what I do is that I try to, so I divide it by 2. Why? Because so the difference signal divided by 2 and we give first one half to this part and the negative half to this part. So, that they are 180 degree phase shifted with respect to one another, and therefore, I would expect to see a maximum gain out of it, right. And we try to find out the value of VD1 and VD2 and then we subtract VD1 minus VD2 or VD2 minus VD1 and I get what is known as VOD, output difference. So, VID means input differential voltage, OD means output differential voltage, right. Assumption again that Q1 and Q2 are perfect transistors and you have a current source which is basically your ISS or the current source here which is given by I, and it is connected to minus VSS on this side, and therefore, this is basically your high impedance node Z equals to infinity at this particular point, and therefore, whatever current is flowing will be equally distributed across this arm and this arm as I by 2 and I by 2. With this knowledge, let me just show, that is what I have shown here, that since this is basically the current is a current source terminating here, and therefore, what I have shown here is that it is not grounded, right. So, it is basically a floating node sort of, and therefore, the overall current will always remain the same in these two arms. So, I by 2 provided the amount of voltage given to Q1 and Q2 are exactly the same, right. Then only we will see that the overdrives are equal and therefore, the same current will be drawn in a respect. So, with this knowledge, let me show you how does it work out in terms of working principles. So, I can safely say that VG1 is equals to VG2 equals to, let us suppose, VCM, right. Let us suppose I have a common mode signal been given whose value is equals to VCM, then I get ID1 equals to ID2 equals to I by 2, right, because you are drawing I current and therefore, half the current will go to left and half the current will go to the right arm. Therefore, Vs is equals to VCM minus VGS. What is Vs? Well, this point is S. So, the voltage at this particular point is nothing but the applied voltage at this particular point minus this difference gate to source will be this voltage, and that is what I have shown here in this. So, VCM minus VGS, then I get I by 2, therefore, current equals to 1 by 2 mu n, right, C oxide W by L, which is the process transconductance parameter we have already seen, this into VGS minus VT whole square. This can be also written as Kn prime to a larger extent, where we can write down V overdrive to be equals to VGS minus VT, as this is known as overdrive voltage, right. It is overdrive voltage which is equals to VGS minus VT. Therefore, I can just replace this and write down half Kn prime, right, into W by L into V overlap whole square. This is equals to I by 2, which means that if you therefore find out I overlap, this 2 and 2 will cancel out, and therefore, my V overlap comes out to be equals to how much? You just check it out, it will be given as I divided by Kn prime into W by L, this thing is square root of this one, where I is the current drawn to this side, W by L is the aspect ratio, and Kn prime is given by mu n into C oxide, right, and I get V overlap to be equals to root of this whole quantity. Therefore, I can write down in such a scenario when Vg1 equals to Vg2, I can write down therefore Vd1 equals to Vd2 equals to Vdd minus Id is I by 2 into Rd, and therefore, I get that which basically means that VO1 and VO2 are exactly the same, and therefore, if you subtract VO2 minus VO1, I will get output voltage to be 0, or I can write down VOD to be equals to 0. So, therefore, any common mode signal, as I discussed in a BJT also, in a MOS device also, the common mode signals gets vanished off because its output value is restricted in this manner. Now, let me therefore explain to you what is known as input common, so input mode range. So, what the idea is also referred to as ICMR. Now, ICMR basically tells me therefore, what should be the maximum input range to ensure that the transistor which you are working is actually working in the active region and going to cut off. So, you have to be very careful that you do not let the transistor go into saturation directly, but right from the active region it goes to the saturation to the cutoff region and vice versa. Now, let me just write down for you and we will explain this later on that VCM max, VCM means the common mode maximum voltage which you can give is basically Vt plus VDD minus I by 2 RD. You know the reason why, because you see VDD minus I by 2 RD, if you look very carefully here, is the voltage at this particular point. This is VDD minus I by 2 into RD is the voltage at this particular point. You add Vt to it, threshold voltage of this device Q1, this has to be the minimum voltage. See, if my voltage falls below this, right, say my threshold voltage is my Vt is say 1 volt and VDD minus 1 by 2 RD is equals to say 1 volt again. So, 1 plus 1 is 2 volts. So, minimum common mode voltage which you should give to the input of Q1 or Q2, assuming they to be symmetric, is minimum is 2 volt. If you keep the voltage less than this 2 volt, then either Q1 will be turned off permanently or you will never get this much amount of voltage drop at your output of your V01, right. And therefore, this is the reason why we define this to be as the maximum value which you see. Now, what is the meaning of VCM min? Minimum is the minimum CM voltage is minus VSS plus VCS plus Vt plus V overlap. Now, obviously this could be grounded also, so this can be put to 0, otherwise it is connected to a negative terminal. VCS is the this voltage which I will just show it to you. This is the voltage which I discussed with you just now. The VCS means this is the S value, right, and this is from this point to this point is the VCS value, which is the voltage across the current source, that is the minimum value, plus what do you require? Plus you require Vt, threshold voltage of the Q1 transistor, and V overdrive. You understand why these two are kept, because otherwise the system will not get on. So, your minimum common mode voltage should be this much that it should be able to switch on the device, draw the device into the active region by V overlap, and should sustain a minimum value of voltage between the source and the through the current source, otherwise this will not work fine. And VSS for all practical purposes is always equals to 0, and therefore I can write down this to be typically equals to VCS plus Vt plus V overlap. So, the ICMR values which you see ICMR, right, should be the minimum value is this much. So, it should be greater than, if assuming VSS to be equals to 0, should be greater than VCS plus Vt plus V overlap, right, and should be less than Vt plus VDD, right, minus I by 2 into RD, fine. So, this is what you get maximum. So, if we delete these two from both the sides because they do not play a role as such, I can safely write down that ICMR, that VCS plus V overlap or overdrive ICMR, right, and it should be greater than VDD minus I by 2 times RD, right. So, you see therefore, if my VDD is high, right, my input voltage should be also going higher and higher, my input common mode range would also go higher. Similarly, if my overlap is high, my ICMR will also go high, and the reason being in front of you that it should be at least greater than VCS plus V overlap. VCS is almost fixed, because assuming that it is an ideal drain current, it is an ideal current source, obviously the voltage across the current source will always remain fixed, and if you add with overlap you get ICMR. So, ICMR is always greater than V overlap in all respects. If you go on increasing V overdrive, you will be increasing the current, and therefore what will happen is this quantity will increase, and therefore this quantity will actually decrease, right, and therefore this will be obviously greater than that decreased quantity. right. So, what people generally do is that they try to make the overdrive slightly larger in order to sustain this relationship in real sense, right. And this is what is ICMR looks like in a real sense of operation. This is again, as I discussed with you, is a small signal model, right, and let us now put a differential signal, input differential signal, and see how it works out. So, what I do, I now put a differential input signal, differential input signal I do, and then what I write down is I refer to as VID, and therefore, my current is equals to 1 by 2 Kn prime into W by L into VGS1 minus VTH whole square, assuming it to be in the active region, and similarly therefore, VGS1 is equals to VT plus 2I by Kn prime into W by L root over. This is equals to VGS1, right. So, that is nothing but Vt plus root 2 V overlap, because if you take root 2 outside, then it is root 2 into root of I divided by Kn prime W by L, that is nothing but V overlap, right. So, I get VID, so I get current to be equals to this much, assuming that half the current is routed through both the arms. Similarly, I get VID max, therefore, VID max input voltage difference should be equals to VGS1 plus Vs. And the reason being that why it should be greater than VGS1 plus Vs is that that VGS1 is nothing but the gate to source of, so gate to source of this is VGS1, right, this is VGS1 and this is Vs value. So, this potential plus this will give you the potential at this particular point, that is what I am trying to say here, that VGS1 plus Vs should be here. If you solve this and do some small manipulation, I get Vt plus root 2 V overlap, right, minus Vt, and therefore, this will come into root 2 V overlap. So, VID max is this much which you get, and therefore, I can which people and now which means that if VID, right, VID if it exceeds root 2 V overlap, then what will happen is that all the current from one arm will be routed through other arm, the other arm will remain almost in the cutoff position, right, and that is the reason you do not write like it to draw it. So, there and VGS1 will be written as Vt plus root 2 V overlap, which means that as Vs will go on increasing, right, Q2 will be switched off. Why? Because let us suppose your overdrive is increasing, right, and your source voltage is also increasing as you move along. If the source voltage is increasing and your drain voltage is fixed, right, then VDS will go on decreasing. Decreasing primarily means that you are forcing the device to go into either into the deep triode region, but that is not my aim, right, and therefore, I cannot let my Vs fall down drastically below a particular point, and therefore, I do not want the Q2 to be fully off, right, and therefore, the maximum value which can be given to a system differential signal is that VID should be greater than equals to root 2, should be greater than less than equals to root 2 V overlap and should be root 2 V overlap. This is the final explanation of VID. So, the maximum, so the differential signal maximum which you can draw is basically minus of root 2 into V overdrive, and this is maximum of root 2 into V overdrive. This is the range of signals, input signals which you can give. Now, the idea therefore is that by giving this such a signal, I am able to sustain it. Anything larger or lesser than this, will force one of the transistors to go into cutoff and other will not go into cutoff in a general sense. So, this is the maximum value of signal which one gets, right. So, let me show to you therefore what is happening here. As you can see, I have biased it, I have VGS1 equals to VID by 2 and VGS2 is therefore minus VID by 2, right, and therefore, this much amount of current is flowing through the system. GM times VGS is basically my ID. So, VGS is nothing here is nothing but VID by 2. So, GM multiplied by VID by 2 is this this current, this multiplied by RD, right, is the voltage across this device. Since this is already grounded, I get V01 to be equals to minus GM RD upon into VID by 2. Similarly, if you look at this side, you will get a GM RD into VID by 2 which you get, right, and therefore, if you subtract this minus this which is V02 minus V01, I get this plus this, and therefore, I get GM times RD times VID, right. Therefore, V01 minus V02 minus V01 by VID is nothing but GM times RD. So, and this is nothing but the voltage gain, because this is the output voltage difference divided by the input voltage difference, comes out to be therefore GM times RD, right, which is exactly what we have already derived in our previous discussion, in our previous slides. So, with this knowledge, let me show to you the large signal analysis here, large signal analysis. In the large signal analysis, what I can write down is that I am assuming that VID equals to VG1 minus VG2. So, if I solve it, I get ID1, I get root of ID, sorry, ID1 is equals to 1 by 2 Kn prime W by L root over into VGS1 minus VT. Similarly, root ID2 to be equals to 1 by 2 Kn prime W by L into VGS2 minus VT. Fine. So, if you subtract ID1 minus ID2 square root of that, right, something will cancel out, and I get root of ID1 equals to ID2 equals to half Kn prime into W by L, right. This is what you get as the overall ID1 minus ID2, and if you do a small manipulation, I get ID1 to be equals to ID2 equals to plus minus, right, I by 2, right, plus minus. So, this is plus minus Kn prime W by L into I into VID by 2, right, and then square root of 1 minus VID square divided by I upon Kn prime W by L. So, just write down for your information sake what I got. I got ID1, right, equals to I by 2 plus I by 2 plus minus Kn prime into W by L into I root over, right, into this is into VID by 2, right, and this is root over 1 minus VID by 2 whole square divided by I divided by Kn prime into W by L whole square. This is your ID1, and similarly ID2 will be with a negative sign, of course, here. Now, for VID equals to 0, which is there is no differential signal, implies that your ID1 will be equals to exactly equals to ID2, ID1 will be equals to ID2 equals to IDD by 2, half the current will flow through this arm. Now, in that case, VGS1 equals to VGS2 equals to VGS, get to source of the first transistor, right, and that gives me a proper idea about where you will be biasing your device in order to get such a figure. So, what I get from this figure, all these discussion is finally I get I by 2, right, I by 2 plus I by V overlap into VID by 2, right, and then I get ID2 to be approximately equals to I by 2 minus I by V overlap, right, VID by 2 I get, which means that the currents which I see are just slightly like they are separated by each other by 180 degree phase shifts, right. So, this is another issue which we have also dealt in BJT when we are plotting the currents versus V overlap by VDD, and you will see that all of them crosses through 0, and then they give something like this. So, the gain actually starts to roll off at higher values of overdrive. So, if you want to sustain a large amount of linearity, it is always advisable to keep your V overdrive to be as small as possible, right, or sorry, as large as possible, right, which implies that W by L should be as small as possible, right, and that is and therefore, the transconductors should be as small as possible. The reason being that GM, when you keep your overdrive voltages very large, right, VGS minus, which means that VGS minus VT is typically very large, which also sustains that your GMs will be also large, and therefore, GM times RD becomes large, which means that the overall gain of the system actually increases drastically. The cost you pay for it is heavy nonlinearity in a real sense. So, it is very heavily nonlinear and gives you a difficult time in terms of understanding the theory behind it, and it is really difficult to get the hold of it. So, what I do, as I discussed with you just now, that if I do a simple design here, which is basically your even your half circuit design, this is basically a half circuit design. I can show to you that using this half circuit design we can actually do it. What is half circuit? Well, half circuits are very standard methodology used in analog circuit design or mixed signal design, where we assume that since the ground and power supply are the same for both the arms, I can divide the two arms into two parts and then just find for one some important term and do a complementary equation for the second one, assuming that they are perfectly symmetrical with respect to each other, and these are known as differential half circuits. Maybe I can just show you. Yes, as you can see, it is a differential half circuit, right. So, this is a differential half circuit which you see here, right, and we will discuss this in detail as we move along, but this is what is differential differential amplifier based design, right. Right. So, with this knowledge or with this idea, let me come to differential half circuits and explaining to you how it works out, right. So, the differential half circuit does what? It divides the whole phenomena or whole devices or whole of the this thing the material or the circuit into two parts. The first part is basically your RD, right, and of course this is the plus VID by 2, half the value of the difference. Then what you do is that you ground it first of all, and then assume that across the drain to source you have R0 here and you have RD here, and then you will have V here and then you have RD here, right, and this is grounded, this is also grounded. Then as you come down you enter into this thing, you have a so this is minus VID by 2 because they are perfectly antisymmetric with respect to each other, right, and therefore this will also have a resistance which is basically given as R0 also in this case. So, this is the half circuit which you see, right, half on the this side, half on the this side. Therefore, I can write down V01 to be equals to minus GM times RD, right, parallel to R0 multiplied by VID by 2. VID by 2 because this is grounded. So, VGS is nothing but VID by 2. So, VID by 2 minus the threshold voltage of the device is the overdrive, and from there I get V01 to be equals to this value which you see, and therefore I get, and similarly VO2 or output voltage 2 will be given as GM times RD parallel to RO into VID by 2, of course with the negative sign changes there. With this knowledge I can safely write down V02 minus V01 which is V0 to be equals to GM times RD parallel to RO, right, into VID, right. So, therefore, if I do a pure differential analysis as such, then what we get is that we get the output voltage difference to be equals to GM times RD parallel to RO into VID, right, and therefore, higher the value of GM, more is the gain which you get at the cost of linearity. So, linearity is always adversely getting affected by a high gain, because when you do a high gain you primarily also increase the nonlinear distortion as compared to your signal, like both of them increase, and therefore it's sort of losing out the whole thing as far as design is concerned. In our next segment or slide we will do some mismatching of RD and GM which we are supposed to do at this part, and then we will discuss about differential amplifier cascoded, and then common mode gains we will discuss, right. So, I think we will stop here at this stage, and next module we will discuss the RD and GM mismatch, as we will also discuss about CMRR and the value of ACM for CMRR equals to infinity. Thank you. Okay, thanks a lot. Thank you very much.